Our next presentation will be from Dr. Phil Lewis on the development of a fuel consumption and emissions taxonomy for non-road diesel equipment. Like John, Phil is on our maintenance equipment committee and very active in the things that we do in the way of equipment. Dr. Lewis is an associate professor in the School of Civil and Environmental Engineering at Oklahoma State University. He teaches courses in construction engineering and project management, and his research focus is in sustainable construction and asset management. He received his PhD from North Carolina State University in 2009. In addition to his academic credentials, he has 14 years of industry experience, including 5 years with the North Carolina Department of Transportation and 9 years with a commercial building contractor. So at this time, I'll turn it over to Phil.
I think John's presentation, I'm glad he went first. So I'm glad I was about a minute late getting here. So John could go first. I think a lot of what he talked about will be a pretty good introduction and match up pretty well with what we'll be talking about today. I was the lead author on this paper. One of our co-authors, Dr. Shan, he's in the back of the room, and Dr. Fitriani, who is our PhD student, she has since returned to Indonesia where she's on the faculty there. So what we'll be looking at today is dealing with heavy-duty diesel equipment emissions. And as was pointed out in our meeting yesterday by Mr. Henry Knight, we know that there are regulations in place for equipment manufacturers to make new engines that have to limit the amount of pollution that is emitted into the atmosphere, especially for nitrogen oxides, particulate matter, carbon monoxide. CO2 is actually a greenhouse gas. It's not monitored or regulated by EPA as a national ambient air quality standard, nor is hydrocarbons. But hydrocarbons is a precursor to ground level ozone, and that is a NAAQS criteria pollutant. And of course, the greenhouse gases, that's one that almost everyone is aware of. In fact, the people will be much more aware of greenhouse gases such as CO2 than they will be any of the other pollutants. So essentially what we're dealing with here is we have about 2 million items of non-road diesel equipment in the United States, and it consumes about 6 billion gallons of diesel fuel each year, and then produces all of this pollution that comes out. And so I think all of that being said, the non-road, the transportation sector is roughly about 25% of all air pollution, and then this non-road sector is probably right around 10% of the transportation sector. So what are some of the impacts associated with diesel emissions? We have health impacts, environmental impacts. So the health, things like allergies, asthma, heart, lung issues. If you have any of these conditions and you're around diesel exhaust, it's a good chance that condition will be exacerbated by just being in the presence of diesel exhaust. And then of course the environmental concerns, smog, acid rain, global warming, all of that stuff. And so as I said, by now many of us already are aware, even prior to my presentation, of what a lot of these issues are that we're dealing with. Here are the regulations that I mentioned. We have both environmental standards and equipment standards. So the environmental standards are these national ambient air quality standards for NOx, PM, CO, O3 and ozone, which hydrocarbons as well as NOx contribute to ground level ozone. And the EPA has recently lowered their standard from about 0.075 parts per billion to 0.070, so they've lowered that standard just recently. So it's a lot of regions, a lot of areas that were in attainment. Well, they were very close to attainment status or in attainment status, and with the new standard, they'll find themselves in non-attainment status. So that means that you have to go back and check every possible source of pollution to try to control that so that you can get back into attainment status. And of course, the regulations right now with heavy equipment by far, by and large, come from the equipment manufacturers, engine manufacturers specifically, Caterpillar, John Deere, Komatsu, all the heavy equipment manufacturers. They have to meet these engine tier standards Right now, a lot of the Tier 4 stuff is finally hitting the road. Tier 0 was basically no regulations. Tier 1, this stuff started coming around in about 95, 96. So these regulations have been around for about 20 years now. And we've been phasing these in over time. And of course, it's based on the engine size of the equipment as to when that standard gets phased in. Some of the current events that we've been looking at, some of the things we've heard just in the last few months. The World something organization, WMO. Yeah, they have, in their recent bulletin, they said that they claim that the global averages of CO2 in the atmosphere reached new highs in 2014. So they're saying we put more greenhouse gas in the atmosphere and it's still there than it's ever been before as long as we've been measuring. And of course, the heavy equipment will contribute to that. Volkswagen, who has not heard about what happened at Volkswagen? Well, if you haven't, they used defeat devices to falsify emissions data. So when they were tested in the lab on an engine dynamometer, it looked fine. They were getting passing results on their pollution test. But then when they go out and run it in the field, it's not working. So it was just a defeat device that only was enabled. It was able to tell the engine was able to tell when it was connected to an engine dynamometer and gave one set of results, passing results. And I believe the last thing I saw said a lot of the results in the field could be 4 or 5 times higher than what the legal limit is, or what the standard is for that. So Volkswagen, they're dealing with something, and who knows? I mean, no one's actually looked at Caterpillar or John Deere or Komatsu to see how their stuff is performing in the field. I actually have some data, so as I get a new student or have some free time, we'll go back and check. At this point, I'm not sure I want to take on John Deere or Komatsu or Caterpillar at this point, but we'll take a look at it and see how our field data compares to what the standards are. And then, of course, I just mentioned about EPA strengthens the ozone standard, so that went from 75 parts per billion down to about 70 parts per billion. And again, a non-attainment status. So if you're in regional transportation planning and things like that, that's actually a pretty big concern for you. So how do we manage this stuff? Of course, one of the first things we have to do to manage anything is to get organized and to classify these things, because we have to know specifically what we're dealing with. So I developed, or I didn't really develop it, I just kind of came up with the idea of having a taxonomy. So what is a taxonomy? It's the process or system of describing the way in which different things are related by putting them in groups. So I just found a couple of examples of taxonomies. This one is taxonomy for information management, and that's just the way they organize things. Any of you who've ever done anything in the educational world, I'm assuming you were all students at some point, if not now. Whether or not you knew it, you were part of Bloom's taxonomy. And so eggheads like John and I, we became quite familiar with this about, hey, we start off down here just trying to give you things that you can remember, and then try to give you things you can understand, and then things you can apply, all the way up to the point that the student is able to create new knowledge on their own. And so that was a way of organizing the way we think and the way we learn. So that's Bloom's taxonomy, and it's quite famous, quite popular in the educational world. And then if any of you who ever had a high school biology class, you've probably seen this, right? And this is the taxonomy of the animal kingdom, Animalia. And of course, I won't try to pronounce all of these, but I thought this was somewhat interesting when I looked at this, or when I tried to remember it, all the way back from 10th grade biology. I could actually go through about the first 3, and then I couldn't remember what came after order and genus. I had forgotten altogether, so I found this, and I said, that would actually be a good way to organize or get started organizing our equipment kingdom. So I went through and just tried my hand at that, and I said, okay, well, what kingdom are we talking about? Well, we're talking about any vehicle that burns a fossil fuel, whether it's gas or diesel. And then the phylum, we can break it down to a little more to just looking at diesel vehicles. And then the class could be heavy duty equipment. And of course, there could be other classes of equipment as well. Instead of heavy duty equipment, they're light duty diesel vehicles. They're even diesel cars. And then also order, we're looking at non-road equipment. The family of non-road equipment could be construction equipment, because non-road equipment could actually be what? A boat. Could have a diesel engine, some marine equipment, and it's non-road, but we want to focus on construction type equipment, such as Caterpillar and John Deere equipment. And then that equipment, you can break it down into track type tractors, or maybe rubber tire type equipment. And then the species would be dozers. So that was just one way I decided to get started on this and get organized. So what we'll be looking at today is a taxonomy of fuel use and emission rates based on the species of equipment. And we'll look at several different species. Now, since we're kind of talking a little bit about biology, we know that diesel fuel is the lifeblood of the equipment. If you don't put fuel in the thing, it's not going to run. Okay, so this is inoperable and it's unproductive. And of course, the equipment is expensive, and the fuel can be quite expensive, and its price is hard to predict. So I found this record of diesel fuel prices over about the last 7 or 8 years. And you can see that it's somewhat volatile. I mean, especially right here from right around in 2009. I mean, we went from close to $5 a gallon down to about $2 a gallon in just a month or so. So you can see in some areas it's very, the fuel prices are quite volatile. Then we had this long period here where we just stayed right around $4 a gallon, and now we're going down again, which most of us like that unless you are from the states of Oklahoma and Texas and maybe a handful of other oil producing states. And right now, these low fuel prices are wrecking the economy of Oklahoma. The university, as any public agency, because they're not getting the tax dollars, we're all facing big budget cuts for the coming year at least. So anyway, the point here being that we can't really predict what fuel prices are going to be. So that's not something you didn't already know. But one thing we can do is we can estimate the quantity of fuel, and there are things in place already that do that. So we're going to try to refine those operations a little bit to help give you better means and methods for estimating fuel use. So a couple of ways to do that. One is fuel efficiency, and that's just the unit of work per gallon of fuel, so such as how many tons or how many cubic yards of earth can we move per gallon of fuel consumed. It's real similar to miles per gallon for cars. So when we talk about fuel efficiency for cars, we're talking about miles per gallon. Fuel efficiency for heavy equipment is maybe tons per gallon or cubic yards per gallon. It can be hard to compute because we have to do pretty intensive field studies. You have to study this stuff in the field, or at least look at the records and the data and hope that those records and data are accurate. And quite frankly, most equipment fleet managers just won't bother with it. Okay, they'll try to look for some benchmark records or published data and use that. And then quite frankly, they really don't want to have to do those calculations either. So now, as the question came up in John's presentation, and John said one thing he may be moving more toward is this concept of fuel burn rate, or fuel use, or fuel consumption. I kind of use these terms interchangeably, fuel use and fuel consumption. To be honest with you, one of the main reasons I felt like the variable FC for fuel consumption was a little more palatable than the abbreviation for fuel use. So that's why I went with FC. So most accurately measured in the field, but this is also time consuming. So this takes a lot of time to measure what our gallons per hour is. And there are ways to do it. If you keep your fuel records with how many gallons of fuel you put in the machine and then check the hour meter, if it's operable on the equipment, you can come up with a pretty quick and dirty number. And so we have this base equation here where FC equals the fuel factor, which is usually given to us by production handbook or some other source of data, multiplied by, which is in gallons per horsepower hour, then multiply it by the horsepower, rated horsepower of the engine, and then multiply that by a percentage, an engine load factor. Okay, so all of that's good. We have a mathematical equation that we can use, so we think it's going to be very accurate, very precise, correct? Well, as Lee Corso would say, not so fast, my friend. What we're looking at here is this is the Caterpillar handbook. Equipment handbooks provide some guidance for fuel factor. I know you can't read these numbers. The intention is not really for you to read these numbers, but this is what we're looking at here. You have this whole column of backhoe loaders. Okay, so anything from a it's like a 416 down to a 450F. Then you have it broken into application, low application, medium application, high application. I think the example I'm looking at is going to be this 420F Tier 2. So in the good old boy units of US gallons, it goes from 0.7 to 3.1 just for a low application. For a medium application, 3.1 to 4.6, high 4.6 to 5.3. But you've got to know if it's going to be a low, medium, or high application, and honestly, a lot of times it's maybe all three. Maybe all three. So really what we're looking at here is trying to estimate fuel uses. We're going from an estimate of about 0.3 gallons, where it goes, 0.7 gallons per hour, up to about 5.3 gallons per hour. So that's quite a range. Now, it's better than no information, I suppose, but we don't really know if it's really all that helpful. Now, that's just estimating FF, the fuel factor. We still have to have an estimate for LF, the load factor. And so this is the initial guidance here, low, medium, and high. And there's some description. So light duty utility applications with intermittent cycles in light to medium soil. And then the high is production applications or digging in rock, dig depths over 10 feet, long cycle times, or regular use of constant flow implements. So yes, this is some guidance. It does help a little bit. But then we have down here the load factor guide. So even if we say, I'm pretty sure I'm working in a low application, well, guess what? You have a range of about 20% to choose from to apply to your load factor. So let's just take a quick look at an example of how this would work. So I've already stated my conclusion here, extremely high variability in estimates of FF and L, or fuel factor and load factor. So here's an example for that 420F backhoe. So that was our range for fuel factor, 0.7 to 3.1 gallons per hour. Load factor ranges 20 to 40%. Therefore, FC, when we multiply that stuff together, it comes out to be 0.14 to 1.24 gallons per hour, and that's a 785% difference. And that's just for that one estimate. So really, are we much better off? I mean, you could probably just ask the operators in the field, how often do you have to fill up? How often do you have to put gas in the machine? And that would be as good as what we have here. But this is what the published data shows us. And this 785% difference representing all of this variability, that's only if we get the application right as being low. What if it's medium or high? Then geez, I mean, you get up well over 1,000% difference in those numbers. And I didn't even go there with it. So one thing that we've done in the past said, hey, just forget all of this stuff up here. Let's don't even talk about it. It's takes too much time and it doesn't really help anyway. Let's just use an average fuel factor. And so what we've come up with for diesel equipment, you can find in most equipment textbooks. So if you take a class on this stuff at college, it's going to tell you the fuel factor is 0.04 gallons per horsepower hour. Okay, and that's, we say, is kind of the average number. So we decided we were going to take a look at that with the data we have and see how that works as an average. And of course, none of this gets back to our original problem of what? Dealing and estimating with the emissions. So all of that stuff with the Caterpillar handbook that I showed, that's only for fuel use. Now, of course, emissions are a byproduct of fuel use. So the objectives of the study is, one, we wanted to look at the efficacy, and that's just a fancy word for saying how effective is fuel factor equals 0.04 gallons per horsepower hour using real world data. So we're going to go back and look at that. One way we're going to do that is conduct an engine modal analysis of equipment data based on a surrogate of engine load using manifold absolute pressure. So we're going to look at the distribution of time, fuel use, and emissions over the full range of equipment engine loads. Then we're going to look at the weighted average fuel use and emission rates based on the amount of time spent in each engine mode. And then we're going to present it all in this taxonomy, or just a chart, a table of fuel use and emission rates based on species of equipment. And that's going to be the end result. So here's a methodology. So the first thing we did in this presentation today is really kind of the culmination of about 6 years of analysis on a data set that I collected during my PhD at NC State. It's a very good data set. It's unique. It's the only one I'm aware of like it. Of course, it is starting to get a little bit aged because most of the equipment topped out at Tier 2, and we would really like to enhance our data set to include Tier 3 and Tier 4 equipment, but it'll take more funding to do that. So we collect real-world data. This data is, is based on equipment that we collected in the field from end-use equipment doing real-world activity. We didn't take the equipment and stick it on an engine dynamometer in a lab somewhere. So this is real-world data. We conduct an engine modal analysis, and so in other words, we just categorized all of our fuel use and emission rates by engine mode, from basically idle to full throttle, and seeing how much time we spent there in each engine mode, broke it down into 10 bins. Then we'll calculate weighted average fuel use and emission rates, and then present this taxonomy. Here's just a quick rundown of the data collection. This is the Axion RS portable emissions measurement system. And what it does is you have a group of sensors that you connect to the engine that will give us manifold absolute pressure, revolutions per minute, intake air temperature, vehicle speed, engine load, and then also, we used a previous version of the Axion RS, but I couldn't find a picture of that one. But it's still the same type of equipment. That instrument cost, it's about an $80,000 instrument. So we connect to the engine, then we also put sample probes in the tailpipe of the equipment, and then we get this conglomerate of data for NOx, PM, HC, CO, and CO2. And this is paired on a second-by-second basis with its corresponding engine vehicle variables of intake air temperature, manifold absolute pressure, and RPMs. So the manifold absolute pressure is what we used as a surrogate for, for engine load, and that's how we did our engine modal analysis. And here's the equation for doing that. We did normalize the data. We just took our second-by-second readings and subtracted the minimum value and divided it by the range of values. So essentially what we ended up with was a range of values from 0 to 100%. And that's how we did that. And this was our hypothesis that we tested. So based on basically the highest average, or in our highest bin of MAP, we were going to compare that average to 0.04 gallons per horsepower hour, and we did a statistical t-test on that to determine if there was any statistically significant difference between the actual average and 0.04 gallons per horsepower hour. Here are the equations for calculating our weighted average fuel use and emission rates. You can see we have Greek symbols in there, and T and I and F and I, no numbers, all letters, and that's how we present things in the academic world. But we won't really spend too much time on this. Really, I can explain it to you better with the sample calculation, but here are the equations. So to get the fuel use and the emission rates are essentially the same thing. So what we were doing is we calculated the amount of time spent in engine modes 1 through 10, and all that was based on those normalized MAP values. We broke those down into 10 separate bins, not equal bins, but based on the amount of time spent in each of those different engine loads, multiplied it by the average of fuel use or emissions rate for that mode, and then you just sum those over the 10 different engine modes. Then down here at the bottom, we were able to convert these are mass per time, gallons per second, or grams per second of emissions. We converted those to a mass per fuel used weighted average in grams per gallons just by dividing the mass per time by the fuel consumption rate. Data collection results, again, a lot of little print up there, but I just wanted to get it up here and show you this. This is all the equipment that we tested. We looked at 6 backhoes, 6 bulldozers, 3 excavators, 5 motor graders, 3 off-road trucks, 3 track loaders, and 5 wheel loaders. And the horsepower ranges, from around 80 horsepower up to the biggest one, I believe, was 285 horsepower. So we have a pretty good range of equipment. And again, most of everything we tested was Tier 0, Tier 1, and Tier 2. And that's where we were with this data set. Here's beginnings of the sample calculations and data. here's the engine modal analysis. And so we broke it down by equipment. So here's the engine mode based on that manifold absolute pressure for each type of equipment that we looked at. And then we just looked at some of these averages for all the equipment. So here's our modal fuel consumption rate, the fuel factor, gallons per horsepower hour for all of our equipment. Here's the amount of time that we spent in each of those modes. And this is just a lot of percentages. But you can see in each case, pretty much in all cases, you can see as that mode, which is the lowest, so would represent just sitting still, idling, a low idle. You spend a lot of time doing that. So just on average, as the engine mode increases, the average time spent in that engine mode up to the highest engine mode at full throttle decreases. And of course, a picture is worth 1,000 words. That table shows you the numbers, but this is what it actually looks like. So here's our modal time and our modal fuel use and our engine modes here. So the solid line, this is the amount of time, and the fuel consumption line is right here. So you can see as that engine mode increases, as we give it more throttle, as we give it more power, and we rev up that engine, the fuel consumption rates increase, a pretty linear increase, okay? But what we saw is that, yeah, out here at this engine load, we have a very high fuel consumption rate, but we don't spend very much time in doing that. And again, that's really not earth-shattering. Most of you intuitively probably figure that out. As far as the time spent in the equipment, most of it is spent out here at these engine loads, and this is a very non-linear function based on our averages that we saw here. So we said we need a way to kind of combine these two. So if we have a high fuel consumption rate, but we don't spend much time doing that, what's the resultant of that? And then over here, if we have a low fuel use rate, but we spend a lot of time doing that, what's the resultant of that? So that was the idea of doing the weighted average fuel consumption and emission rates. And so here's a sample calculation, modes 1 through 10. I think this was for one of the backhoes. So in mode 1, 29% of the time was spent in mode 1. The fuel use rate in gallons per horsepower hour for that for mode 1 was 0.005. We multiply TI times FI and get 0.015. Do that for each of the 10 modes and get a weighted average of 0.017 gallons per horsepower hour for that equipment. Okay. Over here you can see that here's that fuel factor at that highest number is 0.06. So that's higher than the 0.04 gallons per horsepower hour that the textbooks use. Okay, then we did the same thing for the emissions. This was a NOx emission calculation. And so we did that for all of the equipment, and this is what we came up with. Here's our mass per time taxonomy for fuel consumption and emissions. And I'm almost done, Danny. He keeps looking at his watch, so he's too polite to say anything, but I'm almost done here. And so this is, again, the summary of what we've really come up with. And this is mass per time in gallons per horsepower hour for the equipment. And so the way you would use this thing is say, if we want to estimate fuel consumption or pollutant for a tier 1 backhoe or perhaps a tier 2 motor grader, you can just pull the number out of the chart. So hopefully we've refined that original Caterpillar handbook table that I showed you early in the presentation to be a little more useful for the type of equipment, and we've added the concept of pollution here with that as well. So that's our contribution to new knowledge. We also did it on a mass per fuel used basis, so grams per gallon. So if you keep good fuel use records, you may find this table more useful. And the basic conclusions is that when we did our statistical t-test, oh, well, guess what? 0.04 gallons per horsepower hour is actually a valid estimate. There was no statistically significant difference in the averages that we came up with and 0.04 gallons per horsepower hour. So in the absence of better information and you just need a quick and dirty number, you can use that 0.04 and probably get away with it. The modal time has an inverse relationship with modal fuel use. So even though we may spend, we have some very high fuel consumption rates in the equipment, we don't often spend a lot of time at that level. And then the weighted average fuel use and emission rates account for variability in the engine load in the equipment application, so they do not need to be adjusted for engine load. So the one thing with the taxonomies here, you just use these numbers because our data came from real world measurements, so you don't have to adjust these numbers for load factor. We've already done that for you. And then the taxonomy we believe is valid, it's reliable, and you can use it to estimate the energy and the environmental impacts of your equipment if you ever find a need to do so. Questions? So I think you mean, did we look into pairing the equipment to the task?
It would be a separate study, yeah.
Yeah. You know, I mean, I think that would be a great production study. My colleague, Dr. Shan, he's expertise lies in production. I think that would be very good for him. We were looking at this thing originally when we developed the data set primarily from an environmental standpoint. And so, of course, now my experience in construction is you take the piece of equipment you have available and put it over there, even if you only need to dig a small trench and all you have is available is this huge excavator. Well, take the big excavator over there and dig the trench when really all you needed was a little backhoe. But no, I mean, I think you're absolutely right in terms of a strategic and operational analysis. To have an environmental and energy impact, we need to look more into pairing the equipment to the task.
Has the research continued past Tier 2? I mean, obviously.
Well, we only have one item of Tier 3 equipment, so I didn't put that in the taxonomy because usually when you have dealing with data, if you have number of observations equals 1, that doesn't really tell you a whole lot. So we didn't put that one Tier 3 in there. Now I'm actually looking into doing that. We have a heavy equipment. I guess you would, they call it their heavy vehicle institute at one of our sister campuses in Oklahoma, and they have some Tier 3 and Tier 4 equipment. So as time allows, I'll probably go over and try to test some of that and keep going with it.
Okay. Thank you, Phil.
Thanks.